Good morning. Today we are going to see the computed tomography, that is known as CT scan. Everybody knows that CT scan was invented by Hounsfield. He is basically a biomedical engineer from England and who discovered the computed tomography scanner. So why we need a computed tomography scanner? For imaging. Before the computed tomography scanner, we were using radiographic methods with X-rays. So radiography is a two-dimensional imaging. So it will have the difficulty of superimposing the images and it cannot give three-dimensional informations. But unfortunately, all our organs in the human body are three-dimensional nature. So there was a constant search to find out the third dimension of the anatomy. So CT scan came as an answer to that. It not only gives the three dimensions and also it avoids superimposition of images. And apart from that, CT scan also gives very good contrast resolution compared to radiography systems. So in these lectures, what we are going to see is CT scan image quality, how the image looks like, the radiation dose, and the quality assurance what we need for the CT scan. Computed tomography is widely used today in various clinical applications. Though the use of CT is less compared to radiography, the radiation hazards of CT is much more. As it is stated, it produces around 50% of the radiation dose to the patient population compared to this radiography, though the use of CT scan is only 8%. Hence, there is a need to justify the use of CT examination as well as the radiation dose to the patient and hospital workers. The main objective of this lesson is to understand the principle of CT scanner, to understand various factors affecting the image quality and find out the way of improving the image quality. To learn the method of estimating radiation dose in CT scan, to relate the CT dose index with the effective dose to the patient, to explain the various methods of quality assurance for CT scan systems. What is a CT scan? CT scan is basically X-ray imaging system that gives three-dimensional information of the patient. The basic principle is that internal organ of the body can be reconstructed with multiple projections of that organ. It consists of an X-ray source and a detector revolving in a gantry. In general, xenon gas ion chamber or solid-state devices are used as detectors in the CT scan. Nowadays, helical CT scans are used under operation, in which the X-ray tube rotates while the couch is moving. One can vary the speed of the couch, which is normally defined by pitch of the machine. Helical CT scans are operated with the slip ring technology. This facilitates the CT scan now can rotate multiple rotations without coming back to the starting point. The tube voltage ranges from 80 to 140 kV and the tube current goes up to 1000 milliamperes. To provide stable tube currents, high frequency generators are used. X-ray tubes are given with copper or aluminum filters and typical filtration is about 6 mm aluminum. In addition, bow tie filters made up of Teflon are also used. There are 7 generations of CT scans including single slice scanners, electron beam CT scanners, multi-detector CT and dual source CT. Dual source CT consists of 2 X-ray tubes that produce spectra that differ in their average energies. They use 80 kV and 140 kV for data acquisition. Dual CT improves delineation of different material that have similar linear attenuation coefficient. X-ray tube anode heat capacities are very high and can exceed 4 million joules. Power loading on CT X-ray tubes can be as high as 100 kilowatt. So this is the picture showing actually the CT scan. You can see the gantry, you can see the bore, and you can see the patient couch with the monitor and the side table. So coming to the CT image quality, the CT image quality is mainly controlled by 4 factors, namely spatial resolution, noise, contrast, artifact. What is spatial resolution? Spatial resolution is the ability to discriminate between adjacent objects, that is expressed in LP per centimeter. LP stands for line pair. It depends on pixel size, focal spot size, detector size, choice of image reconstruction, filter, and sampling frequency. The range of spatial resolution in CT is spatial resolution in CT is 5 to 15 LP per centimeter. Noise. Noise is the fundamental limit to the quality of the CT image. It reduces contrast resolution of small object and worsens spatial resolution of low contrast object. There are 3 sources of noise, namely quantum noise, electronic noise, structural noise. The quantum noise is the major contributor and is caused by random variations in the number of photons detected. It depends on the selection of technical factors such as MA, scan time, and slice width. Increase of MA and slice width reduces noise but reduces spatial resolution also and increases partial volume effect. Increase of KVP ensures penetration and higher number of photons reduce noise but also reduces the contrast. Reduction of FOV has fewer number of photons per pixel which increases the noise. In a single slice scanner, pitch does not affect noise but pitch reduces dose due to interpolation between rotations and make use of detector photons. In a multi-slide CT scanner, increase of pitch increases noise because of the cone beam effect. Complex reconstruction and data are used from all detector rows for each projection angle. Noise is apparent as window width is reduced, but reveals low contrast details. The typical noise level in CT scan is 3 ounce per unit, and smaller the patient, lesser the noise. Use of detail filter increases the noise and use of soft tissue filter decreases the noise. Contrast. CT contrast is defined as the difference in the ounce per unit values between tissue. Contrast increases if the tube voltage decreases, not affected by tube current or scan times. It increases with the addition of contrast medium. Usually the contrast medium is iodine, and reduces as the photon energy increases. Higher the photon energy reduces contrast much more in high EZ than soft tissue lesions. Lesions that differ by 5 ounce per unit, that is 0.5 5% of mu value from its surrounding can be easily detected in the CT scan. Comparatively, it is around 3 to 5% for screen film combination in radiography examination. Thus, CT gives better contrast than screen film radiography. Narrow window level offers high contrast to the image. Artifact. Here we will see some of the artifacts that come across in a CT scan. Artifacts are the one which not only degrade the image quality but also leads to wrong or misdiagnosis. Some of the artifacts in CT scans are motion artifact, stick artifact, ring artifact, partial volume artifact, spiral artifact, rod artifact, beam hardening artifact. What is a motion artifact? The patient motion is random or unpredictable during the CT scan. The image will display the object motion as a stick in the direction of motion. It depends upon the density of the object in motion, and density is much different from the surrounding produces more intense motion artifact. So this picture shows you the motion artifact caused in the patient. Motion artifacts are more prevalent in scan times of 0.5 to 2 seconds due to involuntary and voluntary patient motion. Structure moves from one voxel to another and introduces errors in reconstruction. Motion artifact appears as double images or image hosting, which may lead to rescanning. Stick artifact. Stick artifacts are due to absence of transmitted X-rays to the detector, and it appears as dark and light bands. You can see the stick artifact in the right side of the image very nicely. The sources of stick artifact are high density material such as metal implant, dental amalgam, and shotgun bullet, etc. Even wearing the ornaments, gold ornaments and silver ornaments by the patient can lead to stick artifact. Stick artifact increase with motion, and metal correction algorithms are provided in some of the CT scans. Beam hardening artifact. Beam hardening artifact or cupping artifact are caused by polychromatic nature of the X-ray beam. As the beam passes through the patient, low energy is absorbed and the mean energy increases. As a result, the beam becomes hardened, that causes underestimation of mu and Hounsfield unit. It is possible to minimize the beam hardening effect by a suitable correction algorithm. Beam hardening artifact are marked at high contrast interfaces, example petrous bones in the head. It is possible to minimize beam hardening effect by suitable correction algorithm. Beam hardening artifact are marked at high contrast interfaces. You can see in the right side picture near the arrow. Ring artifact. Ring artifact is the result of miscalibration or failure of one detector in rotate-rotate system, that is third generation of CT scans. Due to the failure of a particular detector, incorrect data in every projection will appear as a ring in the image. Radius of the ring is determined by the position of the detector in the array and virtually disappeared in the contemporary CT unit. Next, partial volume artifact. The partial volume artifact is the result of averaging the linear attenuation coefficient in a given voxel that is heterogeneous in composition. Example, presence of bone and soft tissue. This artifact increases with increasing pixel size and slice thickness. It is pronounced for softly rounded structures that are parallel to the CT slice. So the right side picture tells you or shows the partial volume artifact. For example, when cranium shares few number of voxels with the brain tissue, there is a loss of details of brain parenchyma. Use of thinner slice and helical scan with the interleaved reconstruction will reduce partial volume artifact. Example, 5 mm slices at the interval of every 2.5 mm will reduce partial volume artifact. Spiral artifact. A helical scan gives an image similar to the partial volume averaging. In one direction, the partial volume averaging is determined by collimation. On the other direction, it is by collimation and table increment for rotation. As a result, instead of a perfect circle, an ellipse-like reconstruction is done. It is more apparent for large beam top angle and large pitch. These bands rotate around the brain as the X-ray tube rotates around the patient. Rod artifact. Rod artifacts are apparent when high contrast objects vary in shape and position. For example, if a cylindrical object angulated with respect to the beam plane, then every projection locates the cylinder at a different position. As a result, the cylinder would appear as an ellipse without table motion. With the table motion, the ellipse gets distorted, extending to surrounding tissues and commonly seen in liver and rib area. Next, we discuss about the radiation dose in CT scan. The radiation dose in CT scan is different in three ways. One, the volume of tissue irradiated by the primary X-ray is very small. Second, the volume of tissue irradiated almost in all angles. Third, radiation dose to the slice volume is higher due to technique used. For example, in a thoracic CT, we normally use 120 kV and 200 MAS, whereas for PA chest radiography, we use only 120 kV and 5 MAS. In the CT scan, the scatter radiation increases the dose than the primary, and the tissue beyond the sections are exposed to radiation. The dose profile is not uniform along the patient axis, and the doses to the patient surface may be higher than the dose at the center of the patient. The surface center dose ratio is in the order of 1:1 in head scan and 2:1 in the body scan. CT section dose profile is not perfectly square but have tails that extend beyond this section edges due to scatter. Dose increases as the number of slices increases. To measure the radiation dose, the concept of multi-slice average dose (MSAD) is used. It is defined as the average dose at a particular depth from the surface resulting from large series of CT slices. It is recommended by FDA USA. MSAD is estimated by measuring CT dose index (CTDI) and dose length product. The dose length product or CTDI is the radiation dose at the center of the peripheral point on a head or body phantom for a single scan from 7 CT slices on both directions. That is, a phantom having 14 slices, center we have to keep a radiation chamber and make measurements. The integral of the axial dose profile for a single CT slice divided by the slice thickness is calculated. Dose is integrated over 14 slices by a 100 mm ion chamber. CTDA are always stated for 100 MAS value. In general, head phantom 16 cm diameter or body phantom 32 cm diameter made up of PM, MA material is used, which is with pencil type ionization chamber to measure CTDI. Measurements are made at the periphery and at the center. CTDA increases with the tube voltage, and CTDA of the body scans are lower than head scan due to greater attenuation in the body. The weighted CTDA is expressed as CTDA-W, which is given by the relation CTDA-W equal to 2/3 CTDA periphery plus 1/3 CTDA center. Once you have the CTDI, Then we can calculate the DLP using CTDI-W into T into N into C, where N is the number of slices, T is the slice thickness, and C is the exposure in mAs. DLP is proportional to the total dose imparted to the patient. It can be used as an indicator of the relative risk of the CT. CTDI does not quantify patient risk. That is the reason we use DLP, that is dose length product. Since slice thickness, number of slices, organ sensitivity are not accounted in CTDI, which are accounted in DLP. Effective dose. CT scan exposure will not produce deterministic effect, but the induction of cancer is the risk. This depends on dose and radio sensitivity of the organ or tissue. The radiation dose increases with the tube current and scan time. To account the radiation risk as well as the radio sensitivity of the tissue, a parameter effective dose is defined. The effective dose, that is H suffix E equal to EDLP into DLP, where EDLP is a tissue specific normalized effective dose in millisievert per milligray centimeter. The typical CT dose index, dose length product, and effective dose values are given in table 1. Effective doses for head CT scan in infant children are 4 times higher than that of adult. Body CT scans in infant and children are double the dose of adult. Children doses higher due to smaller organ size. CT accounts only 8% of the all examination but contribute 48% of the total patient dose from X-rays. So this table gives you the various tissues, head, chest, abdomen, pelvis, and corresponding CTDA-W values in milligray, DLP values in milligray per centimeter, effective dose HE in millisievert. In head, the corresponding values of CTDA is 60, DLP is 1050, and effective dose is 2.4. For chest, CTDA is 30, DLP is 650, effective dose is 1.1. Abdomen, CTDA is 35, DLP is 800, effective dose is 1.2. Pelvis, CTDA-W is 35, DLP is 600, and effective dose is 1.1. The patient effective dose is proportional to the total energy deposited and the dose is proportional to the tube current scan time. Increasing the KVP from 80 to 140 increases the dose by a factor of 5. The effective dose is also proportional to the product of the slice thickness and number of slices. In helical CT, the dose is inversely proportional to pitch. A pitch of 1.5 will reduce the dose to 67% compared to that of pitch 1. Similarly, a pitch of 2 reduces the dose by 50%. Pre and post contrast CT scans of the abdomen doubles the patient dose. Skin doses are very high in CT fluoroscopy. Quality assurance of computer tomography. To perform quality assurance test for the CT scanner, one can follow the radiography quality assurance tests like focal spot size, tube voltage, linearity of MA loading station, timing linearity, output consistency, tube housing leakage. In addition, one has to perform mechanical test, collimeter test, resolution, etc. for the CT scan exclusively. Alignment of table gantry. The concurrence between the gantry midline and table midline is checked using a plumb line. The tolerance should be within plus or minus 5 mm. Scan location, light accuracy. A non-screen cassette is loaded with the film is used for this study. The KVP, MAS and slice thickness is suitably selected. The alignment of internal laser light and the external laser light is checked. The tolerance should be within plus or minus 2 mm. Gantry tilt. A non-screen cassette is loaded with the film is used for this study. A particular KVP MAS is selected in the scanner. The gantry is tilted for a set value and the corresponding tilt is measured. The difference between the set and measured gantry tilt is found. The tolerance should be within plus or minus 3 degree. Table position per increment. A non-screen cassette is loaded with the film is used for this. An initial table position is chosen and the given load is put on the couch. The KVP MAS and slice thickness is selected. The table is set with the different increment from the reference position, say 1 cm, 2 cm, 3 cm, 4 cm and 5 cm respectively. At the same time, the couch increments are measured correspondingly. The difference between the set couch position and the measured is found. The tolerance should be within plus or minus 2 mm. A non-screen cassette is used for radiation profile width. For a given slice thickness, the density of the profile is recorded in the film. This is repeated for different slice thickness. From the density profile, the profile width, that is full width of maximum, is found for each slice thickness. The tolerance should be within plus or minus 1 mm. It is tabulated as given in the table for each slices and the measured density with FWHM. Low contrast resolution, you have to use low contrast resolution test phantom. A given KVP MA slice thickness is set on the scanner. The phantom is exposed for a given window width. The resolution is measured from the phantom in millimeter and the percentage of contrast difference is calculated. The tolerance is 5 mm at 1% contrast difference and the expected is 0.5% contrast difference. High contrast resolution test phantom is used for high contrast test. A given KVP MA slice thickness is set on the scanner. Phantom is exposed for a given window width using high resolution algorithm. The size of the smallest resolver bar per hole pattern is found in millimeter, in mm or LP per centimeter, and the percentage of contrast difference is calculated. The tolerance is 1.6 mm or 3.12 LP per centimeter at 10% of the contrast difference, and the expected high contrast resolution is 0.8 millimeter or 6.25 LP per centimeter. To measure the CTDI, pencil type ion chamber is used. The KVP is set as 80 for MAS of 100. For a given slice thickness, the axial dose, peripheral dose is measured in milligray, then milligray for MAS arrived. Then the KV changed to 100 and 140 with the same MAS and slice thickness, and the measurements are repeated. The procedure is completed both for head and body phantom. The mean peripheral dose is found for both head and body phantom. Then CTDA is found. The tolerance is plus or minus 20%. It is tabulated in the table as given below. CT scan has become a vital tool in clinical medicine and almost no patient goes without CT scan. It offers highest proportion of radiation dose to the public and hospital staff compared to other imaging modalities. There is a need to justify the use of CT scan in general and especially in children as they are more sensitive to radiation.